All right. Hey, everyone. Welcome back to our linear algebra lecture series. So today we'll be talking about similarity and diagonalization. Very fancy words. And these are going to be some pretty satisfying results, I think. But so let's dive in. This will be the last section that we cover in chapter 4. So the idea behind this section is that we really like working with triangular and diagonal matrices. You've seen already that the determinant of matrices like that is just like read it off the main diagonal. For a diagonal matrix, you can take its power just by taking the powers of the entries on the diagonal. That kind of thing. So diagonal and triangular matrices have some really, really nice properties. And we would like to be able to convert in some way whatever square matrix that we're handed into a diagonal matrix of some kind. Unfortunately, we only know one process right now that does that, which is Gaussian elimination. But Gaussian elimination does not preserve eigenvalues, characteristic polynomial, that kind of thing. And so instead, we want some kind of alternative. And so that is where the notion of similarity comes in. So we'll start with the definition of similar matrices. Let A and B be n by n matrices. We say that A is similar to B if you can find some invertible n by n matrix P such that P inverse AP is equal to B. Okay, that's what it means for A to be similar to B. You can find a matrix P invertible such that P inverse times A times P gives you the matrix B. And in that case, we write A is similar to B. Notice that in this equation, you can just multiply both sides on the left by P again. And so to check whether A and B are similar, you can check that these two matrices are the same. This is an equivalent condition, and it's often much easier to verify because you don't need the inverse of P. So if you only had P and you didn't have its inverse, then you can go and you can go and find it that way. Okay. Now, another thing that I want to point out is that similarity is what's called a relation. So a relation is like less than or equal to, or some way of relating two objects in a set. However, it is not necessarily true that if A is similar to B, then B is similar to A. Right? That's not necessarily true. An example of a relation where that's not true is the less than or equal to relationship. So if you have two numbers, A and B, little a, little b, and you have A less than or equal to B, it is not necessarily true that B is less than or equal to A, right? Relations are not that strong. They're just saying that like there's a relationship between two objects, right? As it turns out, specifically similarity of matrices is a stronger type of relation called an equivalence relation. And we're going to prove, one of the things that we'll prove is that if A is similar to B, then B is also similar to A. Well, and I'll show you why as well in just a minute. Now, another thing to notice is that although P does depend on A and B, it is not necessarily unique. In fact, a fun exercise might be to see if you can come up with a strategy for computing matrix P given A and B. This is something that we actually talked about in office hours, and it was just intense. It's not impossible though. I recommend you try it. Okay. So what we want to do right now, real quick, is just verify that these two matrices are in fact similar, and P was handed to us. So we have to verify that 1, 2, 0, negative 1, that's A, times P, 1, negative 1, 1, 1, equals P times B. So 1, negative 1, 1, 1 times 1, 0, negative 2, negative 1. Okay, and this is just matrix multiplication, 2 by 2 matrices, so we'll just do it real quick. 3, negative 1, 1, negative 1 on the left, and on the right, 3, negative 1, 1, negative 1. I almost thought it was a 0. Okay, great. So, and of course, these are the same matrix, which means that A is similar to B, and here's the matrix P. Now, again, if you want to prove that two matrices are similar, you must produce an invertible matrix P, which satisfies this property, P inverse AP equals B, or, AP equals PB. Great. Okay, so here we go. Here's our theorem. Similarity is an equivalence relation on n by n matrices. By the way, an equivalence relation is a relation that just satisfies these three additional properties. These properties have names. An equivalence relation is a relation which is symmetric. That is, A is similar to A. Okay. Reflexive. That is, if A is similar to B, then B is similar to A. And transitive. That is, if A is similar to B and B is similar to C, then A is similar to C. You've seen all of these things show up in some algebra class somewhere, probably. These you may also hear these referred to in like a different word tense. So, like for example, symmetry, reflexivity, and transitivity. This one is the most got the most spotlight out of all of the properties of an equivalence relation, I guess. Okay, anyway, we want to prove these real quick. So what do we have to do? We want to prove that for any n by n matrix A is similar to A, which means we need to produce an invertible matrix such that P inverse AP equals A. I can think of an invertible matrix which does the job. Take P equals I. Well, the inverse of the identity matrix is itself. So this tells us that I equals A, which is definitely true. So here is an invertible matrix which does the job. And so there you go. This relation is definitely symmetric. Probably more interesting is reflexive. So we want to prove, so suppose A is similar to B, then there exists some matrix P invertible such that P inverse A P is equal to B. We want to show that B is similar to A, which means that, so show B is similar to A. Now you might think like, wait, we're done. No, not quite. We need to find an invertible matrix where you can, so we need to find some invertible matrix Q such that Q inverse BQ is equal to A. That's not quite the same as what we're given with by hypothesis, right? We have to go and actually find a matrix Q that does that. Fortunately, take Q equals P inverse. P inverse exists because P was assumed to be an invertible matrix. By assumption, right? When you do this, now just take the equation that we also know holds, and rewrite it as like multiply both sides on the left by P and on the right by P inverse. We write this as, so then we have A equals P B P inverse, which is P inverse inverse B P inverse. But Q is P inverse. So this is just Q inverse B Q. So in other words, B is similar to A, and the matrix that you use is the inverse of the matrix that you use to show that A was similar to B. Okay, it's subtle. They're different, right? Okay, transitivity. Here we go. So suppose A is similar to B and B is similar to C. In other words, P inverse A P is equal to B for some invertible matrix P, and Q inverse B Q is equal to C for some invertible matrix Q, right? So in other words, we now have we have two things that we're using in our assumption. So we're assuming that A is similar to B and that B is similar to C. And now we need to show that there's some matrix R whose inverse times A times R is equal to C. Okay, take R equals, how are we going to do this? R is going to be P Q. Just got to make sure we get the order right. Take R equals PQ. Okay. So now we want to compute what is PQ inverse A PQ. We want to show that this is equal to C. If this is equal to C, notice PQ is definitely an invertible matrix. It is the product of two invertible matrices. So its inverse exists. This should be fine. I want to make sure we get the order. We might end up with the order backwards, in which case we have to go and take something different. But I think this will be right. So now we have a matrix inverse times A times that matrix. If that thing is equal to C, then A is similar to C. That's what we needed to show. And so let's see if it is equal to C. So the inverse of PQ is Q inverse P inverse. And I'm going to also apply associativity here. So Q inverse P inverse A P Q. That's what this product of matrices is equal to. But P inverse A P is equal to B by the fact that A is similar. Since A is similar to B, P inverse AP is equal to B. So this is really just Q inverse B Q. But B is similar to C by the matrix Q. And so this thing is equal to C. And we're done. Okay, great. So equivalence relations. Equivalence relations show up really all the time in math. In fact, if you can find an equivalence relation is a way to break your set into a bunch of groups that are all essentially the same up to the difference of whatever up to inside of the equivalence relation. So in other words, so a good example would be on the set of all fractions. There is an equivalence relation. So the set of all fractions you might think is the set of all numbers p over q, little p over little q, where p and q are integers and q is not equal to 0. However, it's not quite right, Because 3 over 9 is somehow equal to 1/3. It's the set of, okay, so there's in other words, these two things are equivalent up to the equivalence relation on the set of all fractions. I'll just tell you what it is in case you're curious. PQ is equal to P prime Q prime if PQ prime minus QP prime equals 0. That's the equivalence relation. And you can actually play this game, find a bunch of fractions, P over Q's, Q not equal to 0 again, and then check these three properties. So like, for example, P over Q equals P over Q. Is that true? Yeah, because PQ minus PQ is equal to 0. If PQ equals P prime Q prime, then does P prime Q prime equal Q prime equal PQ? And the answer is yeah. You just switch the order of equality. That'll switch the order of this subtraction. But if the two things that you're subtracting are the same size, then you'll still subtract to 0. And then you have to check transitivity as well. But you just have like a P double prime and a Q double prime. You just do all the cross products or whatever, cross ratios. So anyway, so these, but like, okay, if it shows up with similar matrices and it shows up with fractions, you can imagine it's going to show up pretty much everywhere in between as well. So you can define all kinds of gnarly equivalence relations. So that's a really interesting rabbit hole to fall down, which we're not going to do more than that little comment, I promise. Instead, we have theorem 422. So let's just take a look at the types of things that similar matrices have in common. This is great. That's kind of great. So let A and B be similar matrices, n by n. We have the following things that they share. So for one thing, if they have the same determinant guaranteed. Yeah, similar matrices have the same determinant. They are also are invertible, have the same invertibility. I don't know. If A is invertible, then B is invertible, and vice versa. If A is not invertible, then B is not invertible. That's a consequence of the determinant. If the determinant of A is non-zero, well, then the determinant of B is non-zero because they're the same determinant, right? So, and if the determinant of A is 0, so is the determinant of B, right? So, this is just a consequence of part 1 of this theorem and the fundamental theorem of invertible matrices, version like 10 or something. Okay. These matrices also have the same rank, so keep that in mind. They also have the same characteristic polynomial and eigenvalues. That's kind of a really big deal, and we're going to get to that in the rest of this section. We're going to exploit that fact pretty heavily. They also powers of similar matrices remain similar. That's true for positive or negative integers. It's just that if you want to allow for negative integers, you have to also allow that A is invertible. At least A is invertible. But if A is invertible, then B is invertible, right? So Yeah, a bunch of really, really useful facts about similar matrices, and you can use those facts to quickly determine whether certain matrices, are not similar. For example, um, if you have the identity matrix as opposed to this just off from the identity matrix, well, they both of these guys have the same, for example, rank determinant, right? These guys have this. I mean, determinant of these matrices is 1. The rank is 2. What else? They're both invertible. What else? What else do they have? They have the same characteristic polynomial. If you'd have to go and compute that, but notice a minus lambda I, it's lambda minus 1 minus lambda times 1 minus lambda minus 0. That's true here because you have 1 minus lambda times 1 minus lambda, but then you go and minus 1 times 0 instead of 0 times 0. That's still 0. And so they'll still have the same characteristic polynomial, which means they're going to have the same eigenvalues. Okay, wait. Here are two matrices that have all 5 of the first ones at least in common, and yet are not similar. So you have to be careful about similar matrices. It is these properties do not guarantee even if you satisfy the first 5 properties, it does not guarantee that your matrices are similar. And so you just have to be careful. Let's just do some quick checks to figure out if these guys are similar. So we just go and compute determinant of each. I don't know, call the first one A, call the second one B. The determinant of A is 1 minus 4, which is negative 3, but the determinant of B is 4 minus 1, which is positive 3. Since the determinants are not equal, it does imply that the matrices are not similar. That is a logical property called the contrapositive. Essentially, and for those of you who really, really like symbolic logic, if I have some property P that implies Q, then it is logically the same to say that the failure of the property Q does in fact imply the failure of the property P. This is like not. So not Q does imply not P. So, we used that just now. We said, okay, if A is similar to B, then the determinant of A is the determinant of B. Well then, if the determinants of A and B are different, then A and B are not similar. That also has a grammatical sentence that's quite the nightmare. Right. So let's check out this last one. You can check the determinants again. 2 minus 6 is negative 4. Determinant of A is negative 4 here. Over here, for determinant of B, well, the determinant of B is negative 1 minus 3, which is also negative 4. But go and compute their characteristic polynomials. When you do, you'll find that the characteristic polynomial of the first one is going to be like lambda squared. Oh man. Minus 3 lambda minus 4. But on the right, we're looking at just lambda squared minus 4. That has to do with the cross terms when you multiply 1 minus lambda times 2 minus lambda as opposed to 1 minus lambda times negative 1 minus lambda. The cross terms cancel in one case and don't in the other. And so, we're left with different characteristic polynomials and different eigenvalues. even though they had the matrices themselves had the same determinant to begin with. So again, these are all different conditions. That's the point of these examples. They're all different conditions being imposed. I'm not boxing in the last ones because uh, we have like already assumed the fact that these matrices are similar. But okay, great. So that's enough about similar matrices. But once again, wouldn't it be nice if we had a matrix A that was similar to a diagonal matrix? After all, similar matrices have the same eigenvalues, and I know the eigenvalues of a diagonal matrix. It's just the entries on the main diagonal. So if I knew that I had a matrix that was similar to a diagonal matrix, I know the eigenvalues of that matrix. Let me just show you that real quick here. Oh, first of all, definition. A matrix is diagonalizable if it is similar to a diagonal matrix. This concept is important enough that we give it a definition. And actually, it's going to be like diagonalize that word. We're going to use all the different parts of speech that you can apply to that word. It's going to be great. So we call a diagonalizable if it is similar to a diagonal matrix. And now here's an example of that. We're going to show that the matrix 1, 3, 2, 2 is diagonalizable. And the matrix that we use for it is going to be this guy. 1, 3, 1, negative 2. I'm missing a negative sign. Yikes. That was a close one. Okay. Let's just check real quick. The matrix product up here is going to be 4, 4, negative 3, 2. And over on this side, we're looking at 4, 4, negative 3, and positive 2. Great. So these matrices are similar. Notice here's the P, here's the D, here's the A, and then here's the P again. AP equals PD instead of AP equals PB, right? For some reason, I put my equal sign backwards. Okay, well, anyway. But the question is, all right, we still need to slow down here. I keep conjuring this matrix P out of nowhere. And frankly, I also conjured a diagonal matrix D out of nowhere. Where did they come from? Okay, so first, before we say where they came from specifically, we have a characterization of diagonalizable matrices. So an n by n matrix is diagonalizable if and only if it has n linearly independent eigenvectors. Okay, so, okay, let's say what that means. So here's how you construct P and D. The diagonal entries of D are precisely the eigenvalues. Okay, that we already knew because the eigenvalues of a diagonal matrix are the entries on that diagonal, and similar matrices have the same eigenvalues. That was the last theorem that we saw. So the eigenvalues of A must be the eigenvalues of D, but and of course, right, A is diagonalizable. What that means is that A is similar to D, the diagonal matrix, right? So okay, if and only if though A has n linearly independent eigenvectors, what are those eigenvectors? Those eigenvectors are the columns of P. And it's more specific than that. It's in the order that you see them in the diagonal matrix D. So you can switch the order inside of the eigenvalues inside of D. Just make sure that when you have your matrix P that you've constructed by putting the corresponding column vectors, which are the eigenvectors, make sure that the eigenvectors line up with the corresponding eigenvalues in D. So in other words, if x is an eigenvector of lambda I, and lambda I is in column 3 of D, then x better be column 3 of P. Does that make sense? Okay. So now let's prove this theorem. It's going to be great. This is not so bad. We're going to do, so this is an if and only if proof. The reverse implication is the same as the forward implication, so we're just going to do one. But it goes like this. Let P be the matrix. So, okay. Let P be the matrix, P1 all the way up through Pn, where these are the eigenvalues of A. And D will be lambda 1 all the way up through lambda n, this diagonal matrix. Okay, sorry. I almost cheated. These are columns of P. Just columns of P. And what is P? Well, we are assuming that A is similar to D, which means that I'm just going to write AP equals PD for some invertible matrix P. And all we're saying is that we're going to just like let P1 up through Pn be the columns of this matrix P. Then what is AP? Well, this is it's the matrix whose columns are AP1 all the way up through APN. These are going to be column vectors. Just check the matrix multiplication. And each of these columns is a column in this resulting matrix. Now the question is, and so we also know that this is A D, but D is a diagonal matrix. I know what its columns are. It's A lambda 1. By the way, this is just, we don't know that these are eigenvalues. We know that they're the eigenvalues of A because similar matrices have the same eigenvalues. So might as well put them for what they are. A lambda 1, which is just a scaled version of A, sorry. Sorry, what am I doing? I've done the wrong thing. This is going to be confusing. It should be PD, right? That's what we're trying to compute. And by the way, the thing that helped me realize I'd written the wrong thing was that a scaled version of a matrix is a matrix. It's not a column vector. And so in other words, the dimensions were off for my matrix multiplication. So there's something that's always running in the background, which is, are your dimensions of your matrix products correct? Be skeptical at every step to make sure that you've got the right dimensions. It'll save you a lot of backtracking later. Okay, so what we're doing here, so what are we saying? This is really P1 all the way up to Pn, these columns, times D. But I know what this matrix is. You just take lambda 1 times P1. Lambda 1, P1. A scaled version of P1 is the first column of this matrix, and so on. All the way up to the last one is lambda n, Pn. It's a scaled version of the last column of P, and all in between, right? And now let's just look at what we have. AP1 equals lambda P1. And all the way up through APN is equal to lambda Pn. Every single column of P turns out precisely to be an eigenvector of A with eigenvalue lambda I or whatever corresponding to that column. Also, so what are we trying to show? We're trying to show that A has n linearly independent eigenvectors. Well, we have found n eigenvectors. How do we know that they're linearly independent? The columns, or these eigenvectors, are linearly independent. Since P is invertible, why is that true? Because we have a fundamental theorem of invertible matrices which says that just quite literally, the columns of an invertible matrix are linearly independent. But we knew that P was invertible. So we knew right from the beginning, from the very construction, that the columns of P were linearly independent. And this computation shows us that not only are they linearly independent, they're also eigenvectors. So in other words, if a matrix is similar to a diagonal matrix, then it must necessarily have n linearly independent eigenvectors. If you trace this argument backwards, suppose that you had n linearly independent eigenvectors, make a matrix out of them, it is automatically invertible, and then just compute P inverse AP, or actually compute AP and PD, where D is the matrix made out of eigenvalues corresponding to those eigenvectors, and you will end up reversing this computation. But you'll conclude that you get the same matrix either way. But that's the condition that has to be satisfied in order to have an invertible matrix. In order to have A similar to D. And so, but okay, that's in terms of like logic and stuff like that. That's just tracing through our argument backwards. So we're not going to do it again. But it is true. It's an if and only if proof. So there you have it. Okay, so let's diagonalize the following matrices if possible. You may recognize these matrices from the last video. We were computing eigenvalues, eigenvectors, and eigenspaces of n by n matrices. And these two showed up as examples. So if you remember, these had eigenvalues. This first one had eigenvalues lambda equals 1, and lambda 1 equals 1, and lambda 2 equals 2. But E1 was the span of, I'm going to have to remember, copy that. Oh, it was 1, 1, 1. And then E2 was the span of 1, 2, 4. Now here, the problem is, so every eigenvector is a scalar multiple of one of these two vectors, which means if you write down any three eigenvectors in a matrix, P1, P2, P3, we have a problem. Even if the problem is P3 will be a scalar multiple of either P1 or P2. That is our problem, which means that we don't have we don't have three linearly independent eigenvectors, which means that A is not diagonalizable. That's by just applying the previous theorem. What about this other matrix? So this one had lambda equals 0 and lambda equals, is it 1? Negative 2, negative 2. We had E0 was just the span of 1, 0, 1. And then E negative 2 was interesting. It was the span of the following basis. We had 0, 1, 0 and oh wait, I've gotten this wrong. Okay. 1, 0, 1. I got my E0 wrong. There was a 3 or a 2 inside there. I think it was positive 2. Like this. Negative 1, positive 2, 1. Just double check. I'm not totally convinced about this. Let's try this again. E0 is the span. Okay. When lambda is equal to 0, do A minus lambda I. That's just A. Compute the null space of that thing. You'll notice that x2 is a free variable, which means that one of the basis vectors for the null space is 0, 1, 0. But there's another one, which is the one that says x1 equals x3. So it should be like this, 1, 0, 1. Okay, that first part is correct, but we forgot that you could put, zeros on the outside and any number in the middle and multiply by this matrix, and you'll just get the 0 vector every time. So, okay, there's that. But then there's also E negative 2. And this one had some interesting basis vector. It was span of 1, negative 1, 2, 1, I believe. Let's just check that. If you put a negative 1, oh yeah. If you put negative 1 times negative 1 is positive 1, 0 times 2 is 0, and 1 times 1 is 2, 1 times 1 is 1. Okay. 1 plus 1 is 2. And so if you just do A times negative 1, 2, 1, if you just do this matrix multiplication, you're going to get 2, negative 4, negative 2. And sure enough, that's negative 2 times negative 1, 2, 1. So we just double check to make sure this is the right thing. It's 1, so there's only one free variable. So the null space is one dimensional, which means that as long as this is an eigenvector, it will be a basis for the eigenspace, right? Because it's one dimensional. Okay. Whew. Great. So now we have these three vectors. We are going to pretend that they are linearly, that the bases, the union of the bases is a linearly independent set. So let's just take P to be equal to, I'm going to write this in the order that I want. 1, 0, 1, 0, 1, 0. -1, 2, 1. Why did I do that? Well, that's because okay. The reason I chose the order, it looks like I kind of switched these. I mean, the order doesn't really matter, but notice I'm about to have to compute an inverse, which means I'm about to row reduce a matrix, and I want to make as little work for myself as possible. So like I don't want to have to row reduce a matrix and then swap the rows but whereas I could have put the columns in any order that I wanted to begin with. So notice I've got 3 leading ones on the diagonal, and this column is already completely done. So I'm like halfway done row reducing this matrix just by putting the vectors in a sensible order. Okay. Also, I know what the diagonal matrix D is going to be. It will be the diagonal matrix whose diagonal entries correspond to whose diagonal entries are the eigenvalues corresponding to these eigenvectors in this order. So notice these eigenvectors had eigenvalue 0, and this last eigenvector had eigenvalue -2. Yeah, it's a diagonal matrix. Oh, diagonal matrix has zeros off of the main diagonal, right? Okay, it's a diagonal matrix. It's a silly one. That's zeros. It's almost the zero matrix. Not quite. But by the way, the zero matrix is a diagonal matrix. It's just a very silly one. Okay, anyway. Right. And so now, what are we trying to do? We want to find just this. We just want to find the diagonal matrix, or we want to find a diagonal matrix which is similar to A, and then show that it is similar. So what's left is to verify AP equals PD. AP is -1, 0, 1, 2, 0, -2, 1, 0, -1. P is 1, 0, 1, 0, 1, 0, -1, 2, 1. I could compute the inverse of P and then multiply P inverse AP and hope that D pops out. That's more work than checking this matrix product followed by PD, which is 1, 0, 1, 0, 1, 0, 1, -2, 1, -1, 2, 1 times D, which is like zeros everywhere. And just checking the matrix product. So let's do it. This is not so bad. The first one is even harder, and it's still pretty quick. I'm getting 0, 0, 0. Oh, wait. 0, 0, 0. This is going well. And now we actually already did this matrix product. It's going to be 2, -4, -2. These are exactly the things that you get when you multiply your basis vectors by the original matrix. So this is going to be tautologically true. But anyway, now let's just check to make sure that this works. Multiplying a 0 vector by a matrix is going to give you the 0 vector twice. And then the last one, it's just going to be -2 times the last column of P. So 2, -4, 2, -2. They're the same, which means that A is similar to D. Okay, diagonalizing a matrix is the process of finding these two matrices, P and D. Once you've done that, you've proven that A is similar to D. Okay, great. A is similar to a diagonal matrix, right? Great. Okay, I did pull the wool over your eyes at one point. It was right here, right when I said that the columns of this matrix are linearly independent. We don't actually know that for sure. And if you're there, that is the one thing that's still missing from this argument. How do you know that those columns are linearly independent? They came. Okay, we know that these two are linearly independent. We know that this one on its own is linearly independent. But how do we know that like one does not depend on the other ones? I mean, after all, they're all eigenvectors, so maybe one lives inside the eigenspace of another one or something like that. Um, but what if we even had larger matrices, right? We could have some kind of gnarly dependence relationship between the basis vectors of the different eigenspaces. In fact, in order to verify that these columns are linearly independent, you need to do a linear dependence computation, right? C1 times the first vector, C2 times the second, C3 times the third. Solve the homogeneous system and prove that the corresponding matrix is like full rank or whatever, so that the system is consistent with no free variables, right? And that, so unless you want to do that every time, we need a theorem that says that this will always work. And so we do have a theorem for that. So let A be an n by n matrix with distinct eigenvalues lambda 1 up through lambda k. If bi is a basis for e lambda I, that eigenspace, then the union of the bases is linearly independent. So that theorem says that it will work as long as you just take the columns and put them in, you'll get linearly independent vectors. And the solution, the proof for this theorem is exactly what I laid out, but not like one linear dependence relationship or computation every time. It's like once and for all. We're going to do them all at once. Okay. So we'll just get through it, I guess. So here's how it goes. Let bi be the following basis. So it'll be like vi1, vi2, all the way up to v. I have to be careful about my subscripts because this is going to get pretty intense. We'll say vi m k. Okay. What have I done? K is a subscript. I just want to. Okay. It's not so bad. Okay, so this is a basis. Be the basis for e lambda I. So lambda I is one of the k eigenvalues of A. All right. The dimension of the eigenspace E lambda I will be mk, which means that there are k linearly independent eigenvectors inside of this bi. There are mk linearly independent vectors. But like I don't know what this number is, right? This is the dimension of the eigenspace. And all the eigenspaces could have different dimensions, especially if we're looking at like a 14 by 14 matrix. You could have a 4-dimensional eigenspace and then a 6-dimensional other eigenspace, and then a 2-dimensional and 2 1-dimensional eigenspaces, right? Sky's the limit. We can have some pretty gnarly things, and we have to catch all of them with this proof. So that's what all the subscripts are about. The I that I'm using here is just showing that it's corresponding to lambda I, right? And the mk is the different dimensions for different. It's not mk, it's mi. Mi for I running, so I'll just put I equals 1, 2, all the way up to k, like this. Good, good. Okay. Now, what we want, oh, and also, before I do a linear combination, I want to put b equal to the so b is the union. Okay. In the statement of the theorem, I've said this set b, which is the union of all the bases of the eigenspaces. This set b, what is it here? It is, okay, it's the following set: v1 1, v2 1 2, all the way up to v1 m1. I don't know how many. I don't know what the dimension of the first eigenspace is. It's m1, right? Then v2 1, v2 2, all the way up to v2 m2. Again, I don't know what the dimension of the second eigenspace is, but it's m2, whatever it is, and so on, all the way up to the very last one, which is vk1, because there, after all, there are k eigenvectors, k eigenvalues, and corresponding to each one is an eigenspace. So there are k eigenspaces, which means that there are k bases that we're dealing with, right? K bases. vk2, and so on, all the way to the last one, which is vk mk. Again, I don't know what the dimension of the last eigenspace is. I'm just putting it, but it's mk, whatever it is. Now, what do I want to do? I just want to show that this set is linearly independent, okay? Like no, I'm not. This is a lot of setup for something seemingly innocent. So, to that end, suppose C11 V11 plus C12 V12 and all of the in-between stuff, right? All of this other stuff, all the way up to C, actually, okay, so yeah, C K MK, V K MK equals 0. And I want a non-trivial linear combination here. Okay, so suppose that there's a non-trivial linear combination C11 V1 of these basis vectors that gave me the 0 vector. All I'm going to do is insert a bunch of parentheses. Okay, so then, okay, let's write this carefully. C11 V11 all the way up to C1 M1 V1 M1 plus dot 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 plus, okay, so what we're doing is I'm putting in parentheses, breaking up this linear combination by the first index. In other words, collect all the ones whose first index is 1 and put them inside parentheses. And then for first index being equal to 2, put them inside parentheses. And I'll show you why we're doing this in just a second. So C K1, sorry, CK1 VK1 plus all the way up to the last one, CKMK VKMK. Same linear combination, I just broke it up with parentheses. Now, put xi equals ci1 vi1 plus dot 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 plus ci mi vi mi for each value of I. So that all that we're looking at is x1 plus x2 plus dot 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 plus xk equals 0. All I did was rename the expression inside each parenthesis. So again, I haven't told you why I'm doing this. Right, so I've listed out this gnarly long linear combination, and I'm assuming that it's non-trivial. In other words, one of the coefficients, God knows how many there are. Well, actually, I know exactly how many there are. There are n, because A is an n by n matrix, but broken up in this insane way. Right? So we're assuming that one of those coefficients, at least, is non-zero. Now the question is, which one is it? Because each of these vectors can you guess it? Each of these is an eigenvector. It's even better. It's not just an eigenvector, it's an eigenvector inside E lambda I. Like specifically that eigenspace. So like x3 is an eigenvector in E lambda 3. And x12 is an eigenvector in E lambda 12. That's because the way that we broke them up, we took a linear combination of the basis vectors of E lambda 3 or E lambda 12 or whatever. Well, any linear combination of those basis vectors is an eigenvector in that eigenspace. Or it could be the zero vector. It could be that xi is the zero vector. It could be, right? That is a vector which is inside of lambda I, E lambda I. It is not an eigenvector because the zero vector is never an eigenvector. However, every single basis for an eigenspace, so each bi, since it's a basis, it's a linearly independent set. And so the only way to make the zero vector out of it, the only way to make the zero vector out of a linearly independent set is with the trivial linear combination. In other words, all of the CKs or CIs, whatever, in that particular set of parentheses had to have been 0. So in other words, with our non-trivial linear combination, one of these eigenvectors is non-zero. But since one of the eigenvectors is non-zero, it follows that um, that's a contradiction, right? The problem is there's a linear dependence computation, but all of that would tell us that there are two eigenvectors that are linearly dependent inside the same eigenspace. Is that right? Um, well, regardless, instead, oh, okay. Anyway, this is impossible. This is impossible. It would tell us that one of the bases is a linearly dependent set. That would mean that there's a non-trivial linear combination of basis vectors in an eigenspace that gave you the zero vector. That's not possible. Um, and so instead, all each one of these xi's must be zero, which means that each of these coefficients in our linear combination must be equal to zero, which means the only logically consistent um, linear combination of vectors inside of this gnarly set, which gives the zero vector, is exactly the trivial linear combination, but that's the condition for being a linearly independent set, right? So only the trivial linear combination is consistent. So B is linearly independent. The proof is way harder than I thought. So you can go and pretend you never heard any of this, but I do want to double back and box in the theorem itself, because the theorem itself is a really big deal. Um, it says that if you take the union of the bases of your eigenspaces, you will end up with a linearly independent set. And that really, okay, we did it once and it was really, really hard, but it makes it so that whenever we have to do this computation, we never have to double check. Like, oh, wait, I just took the union of a bunch of eigenspaces, bases, whatever. Um, I like, are they linearly independent? Guaranteed every time, right? So yeah, we did a really hard thing once, but it solves you having to solve a system of linear equations every time you want to take a union of bases of eigenspaces. Okay, great. By the way, I mentioned this in the video for 4.3. If an n by n matrix A has n distinct eigenvalues, think about what that means. That means that it has n distinct eigenspaces, each of which would have to be precisely one dimensional. Think about that one. Which means that each one has a basis of a single vector. All of those vectors union together make a linearly independent set of n vectors, and thus A is diagonalizable. So if you ever find yourself in a situation where you have an n by n matrix that has n distinct eigenvalues, then you automatically have a diagonalizable matrix. That's pretty nice. So for example, um, 1, 2, 3, 4 on the main diagonal, uh, and some, you know, some upper triangular matrix like this. For an upper triangular matrix from the last section, the eigenvalues are the numbers on the main diagonal. So in other words, the eigenvalues of this matrix are 1, 2, 3, and 4. It's a 4 by 4 matrix, which means, since we have 4 distinct eigenvalues, this matrix is automatically diagonalizable. If you turn this 1 into a 2, it's out the window. This is like, we don't actually know if it's diagonalizable or not. We have to do a computation. That's a problem. So to solve that problem, we have the diagonalization theorem. And this will be the last theorem that we have, and then we'll have one example and call it. It's getting to be a long video. So the diagonalization theorem needs a bit of setup. So what is the situation? So the situation is not bad. I just broke our happy example where we had 4 distinct eigenvalues, and I made it so that we only had 3 distinct eigenvalues. But in the example that we saw previously, there were only 2 distinct eigenvalues, right? It was 0 and -2 were our distinct eigenvalues, and yet the matrix was still diagonalizable. So the question is, when is a matrix diagonalizable? Like, we still don't know that answer. We know sometimes when it is, but like, what is the condition for being diagonalizable, right? It can't be just having n distinct eigenvalues, because we have a counterexample of that. So what is it? We actually have to build up to it. So let me just tell you this lemma, and the next lemma and proof and theorem, I'm not going to give proofs for, I promise. So let A be an n by n matrix. Then every single eigenvalue of A has geometric multiplicity. At most, it's algebraic multiplicity. In other words, you can have a high algebraic multiplicity and a low geometric multiplicity. You know, algebraic multiplicity 4, geometric multiplicity 1 or 2 or 3 or 4. But you will not have an algebraic multiplicity of 2 and a geometric multiplicity of 3. That's what this is saying, that the geometric multiplicity is smaller than the algebraic multiplicity. Okay, how does that help us? It's because we have 3 equivalent conditions. So if lambda 1 through lambda k are the eigenvalues of A, n by n matrix, then A is diagonalizable if and only if the union of the bases is linearly independent, which is true if and only if the algebraic multiplicity of each eigenvalue is its geometric multiplicity. Sorry, not linearly independent. This is not right. The union of the bases of eigenspaces of A contains n vectors. We need all n vectors to show up. Otherwise, we don't have a basis of. Otherwise, we don't have enough vectors in order to span the entire space. So, contains n vectors. And that was true in our previous case. Notice we had 2 vectors in E0, I think it was, and we had 1 vector in E-2. And the union of those 3 vectors was a linearly independent set, right? But in particular, it contained 3 vectors, and that's what we needed. That was the condition that we needed. But those 2 conditions are both equivalent, amazingly, to the condition that the algebraic and geometric multiplicities of every single eigenvalue line up perfectly. If that's the case, then you're guaranteed to have a diagonalizable matrix, right? And if you notice, the algebraic multiplicity of lambda equals 0 was 2. It was, yeah, and the algebraic multiplicity of lambda equals -2 was 1. And then for both of these, it was same for the geometric multiplicity. For the exam, you should know how to compute the algebraic and geometric multiplicities of every eigenvalue. It's not bad. Let me remind you, the algebraic multiplicity is the multiplicity of the root of the characteristic polynomial. In other words, if you have characteristic polynomial lambda minus 1 squared times, I don't know, 2 minus lambda, something like this, then lambda equals 1 has algebraic multiplicity 2, because you just look at the exponent here. And so algebraic mul 2. And lambda equals 2 has algebraic multiplicity 1, because the exponent, again, is just a 1. So that's how you compute the algebraic multiplicity. Geometric multiplicity is just the dimension of the eigenspace. That's it. Okay. Great. Okay, so we have one last problem that we'll work through. This is a really gratifying example. So we're just going to compute a to the 10th of some matrix. You have two options. You can either well, okay, this is at the end of the diagonalization section. So like probably diagonalize the matrix first, and then right, we'll go and then find some way to exploit the diagonalization, or just go and multiply this thing by itself 10 times. But I warn you, I can make it harder very easily. So okay, great. So just keep that in mind. I'm going to go the diagonalization route. So notice that if A is diagonalizable, then you can write it as P inverse. So A to the 10th is P inverse to the 10th. So let me just write that again. Okay, dot, 10 times P inverse. Right, this is because P inverse A P equals D. Right, that's where it came from. If A is diagonalizable. We don't actually know that it is yet. I'm just saying it will be because we're in the diagonalization section. That's cheating, but okay. Right, notice by associativity, I can just drop the parentheses and reapply them in any order that I want. And every time I do, notice the inside p's all get paired with their inverse. So they all cancel. So what's left is a to the 10th is p times d to the 10th times p inverse. Multiply d by itself 10 times, and then have a p on the front and a p inverse on the back. So if we can compute p and d, notice d to the 10th is very easy. You just take the 10th power of all the eigenvalues and just put them on the main diagonal in the right order. P and p inverse are also very easy once you've done the eigenvalue computation. So let's go and do it. Okay, a minus lambda I, determinant. I'm going to skip a lot of steps here and just write 2 minus lambda times -4 minus lambda times 6 minus lambda plus 24. How did I do that? Okay, I'll tell you what just went on. Cofactor expansion along the first column. right? What happens, oh, of A minus lambda I. So first thing I did was put a minus lambda everywhere, right? Then I did cofactor expansion along the first column. That's where I got this 2 minus lambda times -1 squared, which is 1. And then times the determinant of the remaining 2 by 2 minor, which is AD minus BC. Here's your A, here's your D, here's 3 times 8 is 20. 3 times -8 is -24, but it's minus BC. So minus -24 is plus 24. Determinants aren't so bad once you've done a lot of them, but keep practicing determinants, please. It's very important. Speaking of practice, this polynomial will factor as negative lambda times 2 minus lambda squared. How do I know that? FOIL this, you get lambda squared minus 2 lambda minus 24 plus 24, minus 24 and plus 24 cancel. So you got lambda squared minus 2 lambda, which is the same as 2 lambda minus lambda squared, all times -1. That's where this minus sign came from. Then you can also factor a lambda. And so this is going to be minus lambda times 2 minus lambda times 2 minus lambda. And so 2 minus lambda gets squared. Set that equal to 0. You get lambda equals 0 and 2. Let me just check algebraic and geometric multiplicities. So the algebraic multiplicities and the geometric multiplicities of lambda equals 1 and lambda equals 2. Sorry, lambda equals 0 and lambda equals 2. When lambda equals 0, the algebraic multiplicity is just 1, which means that the geometric multiplicity, because it's an eigenvalue, it will be always at least 1. So the geometric multiplicity is going to be precisely 1. It's going to be less than or equal to 1 and greater than or equal to 1. It's 1. The algebraic multiplicity of lambda equals 2 is 2. The geometric multiplicity, we don't know yet. We have to go and compute an eigenspace. I'm just going to put that off to the side for now. Okay. Let's compute E0. We're going to need to anyway. E0 is the null space of A. Oh, sorry, it's the null space of A minus 0I. So A minus the 0 matrix, which is A, right? Null space of that, but notice, so this is this, okay, we'll do this one. 2, 0, 0, 12, -4, -8, -6, 3, 6. Oh, augment with 0, 0, 0. And we're going to compute basis for the null space. Okay, here we go. So know that there's going to be okay. We're just going to row reduce the matrix real quick. So divide through by -4. 1 and -3/4. This is why we show our work. But I am definitely skipping a lot of steps. So 1, 6, -3. Adding straight upward, I think we can just zip to the row reduced echelon form, reduced row echelon form. 1, 0, 0, 0, 1, 0, 0, -3/4, +3/2. So E0 is going to be the span. Notice there's one free variable, so that confirms that our geometric multiplicity is 1. Geometric multiplicity is the dimension of the null space, which is also the number of free variables, right? So span of 1 3/4, 3/2. But I kind of hate that number. Look at that. It's like got fractions and stuff. But remember, we can just scale these eigenvectors to get whatever basis vector we want. So I'm going to multiply through by 4. So make it 6, 3, 4. And just for kicks, let's multiply that by our original matrix to make sure that we get the 0 vector. When you multiply 6, 3, 4 on the right of A, you get 12 plus, -6. Because when you set x1 plus 3/2 x3 equal to 0, you get x1 equals -3/2. So I missed a minus sign. Well, there we go. Okay, so -12 plus 36 minus 24 is 0. 0 minus 12 plus 12 is 0, and 0 minus 24 plus 24 is 0. So this is a basis. This is the basis or a basis of E0. Again, notice one-dimensional, so the geometric multiplicity is 1. E2. Okay, this will be fun. This is going to be the null space of A minus 2I. So let's go and write down the matrix that we're going to want. I'm going to subtract 2 from the main diagonals here of A. So, oh great, 0, 0, 0, 12, -6. And then we've got -6, 3, -8, 6. Sorry, -8, 4. So we have to subtract 2 from that 6, right? Augment with 0, 0, 0. Oh, well, this is going to be very fast to row reduce. You just zip to the end. 0, 0, 0, 0, 0, 0, 0, augment 0, 0, 0. Okay, and then the first row we can divide through by, I guess, by 12, if we want it in reduced row echelon form. You should double check if you're not comfortable still with row reduction. You should row reduce all of these matrices the right way so that you can verify and confirm your answers, right? I'm doing them fast because I'm sure, I mean, as much as you love hearing me talk, I want to get to the end of the video. Okay, so what we're left with is, notice x1 is free, x2 equals 1/2 x3, and x3 is free. So E2 is the span of 1, 0, 0 and 0, 1, 2. Okay. You can check those by multiplying back into the original matrix A. I promise it'll work. And now notice that we now have a formula for P and D. P is going to be 1, 0, 0, 0, 1, 2, -6, 3, 4. D is going to be the corresponding, it's going to be a diagonal matrix whose diagonal entries are corresponding eigenvalues. So both of these first two columns were basis vectors for E2. So there are 2's on the main diagonal. And the third one was a basis for E0. And we still need to compute P inverse. And to do that, we have to compute the inverse of a matrix. If you remember that from, I don't know, like 600 years ago or something. Negative 6, 3, 4. Augment with the identity. And just get to work row reducing. I'm going to do this again in a kind of janky way. So first things first, subtract 2 row 2 from row 3. You'll get a 0 here, a negative 2 here, and a negative 2 here. Then we can multiply row 2 by negative 1/2. So 1, 1, negative 1/2. And then, I guess that we just pivot around this 1. So go straight up. We have to take negative 3 row 3 from row 2 and add 6 row 3 to row 1. Take away 3 row 3 from row 2. Okay, so that'll put a minus 2 here. And it will put a positive 3/2 here. And if I want to add 6 row 3 to row 1, okay, I'll get zeros here, of course. And in these spots, I'll get a 6 and a negative 6/2, so negative 3. Great. So let's go like this. P inverse is this matrix. Technology is very nice for this. Okay, so now a to the 10th is p d to the 10th p inverse, which we now have matrices p, d, and p inverse. So this is 1, 0, 0, 0, 1, 2, negative 6, 3, 4 times, d to the 10th, let me just write that down, 10, 24, 0, 0, 0, 10, 24, 0, 0, 0, 0. Oh yeah, the raising to the 10th part of this whole discussion is an afterthought suddenly. And so if the rest of this discussion has other applications and becomes something that you've practiced a lot, now suddenly the raising things to a power is just like, okay, I guess we have to do that too or something. 1, 0, 0 for p inverse, 6, negative 2, 1, negative 3, 3/2, negative 1/2. I guess we just go and do the matrix multiplication. The first two matrices I think are going to be easier to multiply, so let's just do them. 10, 24, 0, 0, 0, 10, 24, 20, 48, 0, 0, 0. Times 1, 0, 0, 6, negative 2, 1, negative 3, 3/2, negative 1/2. And now we just do it. Okay, this one's a little bit, 10, 24, 0, 0. 6 times 10, 24, 61, 44. Because, like, okay, anyway. Negative 2 times 10, 24 is negative 20, 48. And negative 2 times 20, 48 is negative 40, 96. And this last one, negative 3 times 10, 24 is negative 30, 72. 3/2 of 10, 24 is going to be half of the number we just computed, but make it positive. So positive 15, 36. And negative 1, and 3/2 of 20, 48 is twice that number, which is just positive 30, 72. Take a look at those numbers and imagine yourself having actually done this problem by taking a and multiplying it by itself 10 times. You would be doing gnarly arithmetic like that last product, but like dozens of times. So you get to pick which one you prefer more. But again, imagine it's a 4 by 4 matrix and we're raising it to the 20th power or the 30th power, right? And so, yeah, so it's still less time consuming. Even if you're using a calculator to do the arithmetic, it's still less time consuming to use it to diagonalize the matrix first and then raise it to its power. Okay, so this has been a long video, but this is the end of the line for chapter 4. Next time, we're going to start up with chapter 5, which is orthogonality in Rn. And I will see you in the next video.